Okay, this last example for this session is going to push a little bit further, but we want to consider uh, a system consisting of water, H2O, that is initially at 100 kPa and 200 degrees C. So that's, if you think about that, that's atmospheric pressure, 200 degrees C, twice normal boiling point. That's a superheated vapor, but we can confirm that by looking in the tables. That superheated vapor is compressed by pressing that piston down. We're compressing it so the pressure is not constant. We're going to be raising the pressure by compressing this steam. We're going to compress it until the specific volume is 0.4175 meters cubed per kilogram. Now, we need to know something about how this compression is achieved. And what's given or known about this process is that this is a polytropic process with the exponent n equals to 0.84. So that polytropic, by the way, means that PV raised to an exponent is equal to a constant. So what we're asked to do here is to find the final pressure, the work that's done in this process, and then sort of as a bonus or pushing ahead a little bit, we'll go ahead and consider the first law of thermodynamics and see if we can calculate the heat that's added, the amount of heat transfer that occurs during this process. So here we go. We know the initial state, and we can confirm we need two property coordinates about each state, and we know the pressure, and we know the temperature. So this pair of property coordinates should allow us, we hope will allow us to find any information that we need to know about state one. So in my thermotables, I'm finding at 100 kPa, which is 0.1 MPa, and 200 degrees C, I find the following information. That specific volume 1 is 2.1724 meters cubed per kilogram. And I'm going to go ahead and write down internal energy 1 is equal to 2658.2 kilojoules per kilogram. Okay, and I don't need this immediately, but we will need it in the final analysis here as we consider this question of how much heat transfer is required. Okay, sorry, let's straighten that up a little bit. There we go. Okay. So to address this initial question, we need to precisely identify this second state, and by that I mean we need two property coordinates that we can use to locate the second state. We know one of them. We know the specific volume. However, we also know this relationship, this path that leads us from state 1 to state 2. And so by following this path, using this relationship, we can tie the unknown property in the second state, pressure, to the information from the initial state, pressure and specific volume. So let's use the process line to find state 2. So we're going to connect state 1 and state 2 using this process line. And it's sort of like thinking about if you know the coordinates that you're starting from and you know which direction you're going to proceed, you now just need to know how far along that direction do you need to go to stop, to find that state. So the relationship we're going to use is P1 V1 to the n is equal to P2 V2 to the n. And we're trying to find P2. So P2 will be given by the P1 multiplied times the ratio V1 over V2 to the n power. I mean, that's the way the algebra works. When we bring this over to the other side, we can take the ratio and raise it to that exponent. So P1 is 100. V1, we looked that up in the table. V2, we were given and this exponent n is equal to 0.84. So I don't know if my calculator gives numbers that big or not. Let's see if I have that possibility. Yeah, I have a possibility to calculate exponent, so let's try that. Let's see, I need to take 2.1724 and divide it by 0.4175, and that result I want to raise to the power of 0.84. All right, I'm sorry, my calculator's not quite as sophisticated as I hoped it was. Let's try it one more time. All right, 2.1724 divided by 0.4175. Yeah, so when I multiply that times 100, I get 399.64. And by contrivance, I mean, this is really 400 kPa, right? So the answer to this first question that was put, what is the final pressure? The result of 400 kPa is what I would report, 399.65. Let's call it 400. Okay. I guess a good question. So now we can say that state 2 is fixed by the coordinates 400 kPa and a specific volume of 4175 meters cubed per kilogram. So with those two coordinates, we can find that second state. I'm going to go ahead and do that. To push a little further, we need to know the internal energy at that second state to answer this last question. So let's go ahead and do that. If I look in my thermotables at 400 kPa, I'm looking for specific volume 0.4175. And as a first guess, I'm going to go to the saturation tables and see where 4175 lies relative to the VF and VG. What I find out is at 400 kPa, VF is equal to 001084 and VG is equal to 462.42. and I left the units off out of laziness, but 4175 is less than this and greater than that, so therefore we have a two-phase mixture. And so x2 is V2 minus VF over VG minus VF. And I'm going to save us both writing those numbers down twice. I'm going to try to calculate it using my simple calculator here. V2 is 0.4175. And let's see, 0.46242 minus 0.9026. And now I want to immediately use this number to calculate the internal energy at state 2. Oops, U2 is equal to UF plus X2 UFG. And I can get these numbers from my table. .604.22 plus 0.9026 1948.9. And again, turn into my trusty phone calculator. I get 2363.3. Okay, so I think we can answer these last two questions. The work from 1 to 2, which is the work from 1 to 2 divided by the mass, we can find from the integral of P dV. And in an earlier video, I went through the math on this to substitute in P from this form as a constant divided by V to the n and integrate this out. What we find this to be is P2V2 minus P1V1 divided by 1 minus n. And so if we follow the formula here that we came up with, P2 is 400 kilonewtons per meter squared. Specific volume 2 is 0.4175 meters cubed per kilogram. Minus pressure 1 is 100, and specific volume 1 is 2.1724. And we've got to remember to divide this by 1 minus 0.84. Okay, so we can run those numbers out. And I get minus 314. What? Well, I'm going to end up with kilonewton meters per kilogram, and that's kilojoules per kilogram. Okay, the bonus part of our presentation is to find out how much heat transfer is needed. Well, if we consider our first law for a closed system, that we can write the initial energy plus energy added, which we will designate as heat being added with a positive sign, is equal to any energy out, which we'll designate as work being done by the system, plus the final energy. As we have noted before, for a stationary system, a system that's not moving, this piston and cylinder arrangement is sitting still, the initial and final velocities are the same, 0, and there's no elevation change. And so we can see that the heat transfer to the system will be equal to the work plus the increase in internal energy of the system. And I think we have everything that we need to perform this calculation. We found the intensive properties, internal energies 1 and 2, based on the state coordinates that we identified earlier. And so with this information, we can put the work done is minus 314 kilojoules per kilogram, with the minus indicating that it's work done on the system, not by the system. The final internal energy we calculated as 2363.3, and the initial internal energy we found earlier, I'm looking for it, from the tables, 2658.2. And when I put all of this into my simple calculator, let's see what we come out with. 2363.3 minus 608.9 kilojoules per kilogram. Okay, so to summarize, we, in this problem, used some information about the initial state, those property coordinates, fixed that state, and we knew something about the path going from state 1 to state 2. And we know one thing about the second state. So we used the path information, the direction in which to travel away from state 1, and the final information from state 2 tells us how far to go down that path to determine the second state, the coordinates we need for state 2. And once we had those coordinates for states 1 and 2, then we can find any properties that we want to know about those states. As an example, the internal energy for each state can be found. And that information becomes useful to calculate to calculate quantities with the first law of thermodynamics. But in order to find the work done during this process, we needed to evaluate the boundary movement work integral of P dV. And for this polytropic process, with n different from 1, it's P2 V2 minus P1 V1 divided by 1 minus n. We calculated the specific work that's needed to be done, that's done on this in this process. And then finally, we did write the first law, conservation of energy, for this control volume, for this constant control mass, I should say, and found that the heat transfer is the work plus the change in internal energy. All of those are negative quantities, and so the heat transfer is away from the system. Heat is lost from the system, not added to the system.